Today I'm going to be talking about a particularly cool piece of offensive technology that was disguised as a piece of defensive technology that who knows what. So what we're going to be talking about today is the science of kleptography. How many of you guys have heard of kleptography, the word kleptography in the past? Okay, so a little bit of background. So the definition of kleptography is roughly the study of stealing cryptographic secrets securely and subliminally, which does not by itself say a whole lot about what that means. What it really means is building cryptographic systems where some party who probably designed the system can steal information from it without anybody else knowing this is possible or in fact, actually being able to do it themselves. The term was introduced by Adam Young and Modi Young back in 1996. And really up until recently, it was believed that this was mostly kind of a matter for academics to worry about. It was a neat idea, but nobody would ever do it. The only exception we can really think of is a few crypto viruses, crypto locker, that kind of thing. But in 2013, really just a few months ago, everything changed. And I'm sure you guys have all seen this before, but the big change was this, was the publication of a document by Edward Snowden and by the New York Times and ProPublica describing something called the SIGINT enabling project. And this was a top secret NSA project to, and let me give it to you in their own words before we go there. The SIGINT enabling project actively engages the US and foreign IT industries to covertly influence and/or overtly leverage their commercial products' designs. These design changes make the systems in question exploitable through SIGINT collection, e.g. endpoint, midpoint, etc., with foreknowledge of the modification. To the consumer and other adversaries, however, the system's security remains intact. So that's SIGINT enabling. Now let's get specific about what that means. One thing it means is inserting vulnerabilities into commercial encryption systems, IT systems, and so on. Another thing it means is influencing policies, standards, and specifications for commercial public key technologies. And of course, we have to do this very subtly so nobody knows what's going on. There was another specific allegation contained within the documents related to this, and that was that in 2006 or so, NIST published a specification for a random number generator design called the NIST SP800 standard. And that standard, according to these documents, is alleged to contain some kind of fatal weakness that was later discovered in 2007 by research cryptographers. According to the documents, the NSA wrote the standard and aggressively pushed it on the international group ISO, privately calling the effort a challenge in finesse. That's their word for it. So what I want to do is I want to talk about this. Now, you've all heard a bit about this, but I want to get into some details, and I want to talk about some new work that we're presenting on Thursday that talks about how these kind of things work. To do this, I need to go back in time a bit. We need to talk about how we got here in 2014. And to do that, we have to take essentially a time machine back to the early 2000s when all of this stuff began to come into existence. Okay, so in order to talk about any kleptographic system and how we build it, we have to really break it up into three components. The first component is how do we design a kleptographic system in the first place? So the question we have to ask is how do we build a system that many people are going to use and implement, and how do we make it so that we, that is the NSA, are going to be able to extract information from this system without anybody else being able to do so? In the early 90s, there was a protocol or a plan called Clipper. You guys probably remember Clipper and Capstone and those things. These were devices, physical devices that the NSA and the US government was going to manufacture that were going to have built-in key escrow. And because they were hardware, everybody was going to have the same device, and you could control what was going on inside that device, and you could actually build in key escrow as a feature. But you can't do that unless you can mandate hardware. And we can't mandate that everybody in the world has the same piece of cryptographic hardware in their computer, can we? Well, now we can, but maybe we couldn't back then. So what we need to do is we have to build something that can deal with that problem. But we have a second problem, which is that the cryptographic protocols people are using have already been designed and deployed, things like IPsec and TLS. We can't start from scratch and wipe the slate clean with those either. We can't mandate what software people are going to use because software is whatever people choose to implement. We mandate something, they'll just use something else. The two things we can mandate are the design of cryptographic standards and algorithms contained within those standards. And separately, we can evaluate people's implementations. We have programs in the United States called, we have a program called the Cryptographic Module Validation Program, CMVP. And its job is to, if you want to build something and have it FIPS certified, they will take apart your implementation and make sure it conforms to the spec or their interpretation of the spec. So we have some power over what people are going to implement. And so when you start to think about all these limitations, it becomes very obvious where you're going to put your vulnerability or your trapdoor, your backdoor. You're going to target the Achilles heel of every cryptographic system, which is the need for random numbers. Just to give you an idea, most cryptographic protocols, really, they're starving for random numbers. This is a particular measurement of the elliptic curve Diffie-Hellman plus ECDSA TLS mode or cipher suite. It requires at least 108 bytes of random numbers on each connection, and that's on the server side only. So these protocols require a lot of randomness. They require good random numbers, and those numbers may be a bit low, actually. The quality of those bits is incredibly important, but more importantly, if we as an attacker can predict what those bits are going to be, the future bits that this generator outputs, there is virtually no cryptographic protocol that can stand up against us. Doesn't matter what it is, we can break it. So this is the obvious place to put things in. Now, one of the neat features of random number generators is that in practice, they're used for a lot of different things. We use them to generate nonces that go over the wire, but then in the next breath, we'll use the same random number generator to generate very, very secret keys, like ephemeral Diffie-Hellman secrets. And we'll do this thing with the same random number generator, literally 16 or 32 bytes apart. This is an example of an OpenSSL connection where a series of random output blocks have been broken up into a session ID, a server random nonce, which is published, and then an elliptic curve Diffie-Hellman secret key, just to show you how this works in most implementations. So now we have our target, and we need to build an RNG that we can exploit. So I'm going to give what I think is a pretty short primer on how to build random number generators that are kleptographic in nature. So the first thing you need to understand is the architecture of a random number generator. Most people, when they think about this, and historically when they think about random number generators, they picture something like this. There's some kind of random number generator up here. Maybe it's actually spinning a bunch of balls around. Maybe it uses a diode. Who knows what it uses, but it produces a bunch of stuff. And then the bits come out of it, and they go to your crypto protocols where they get consumed. The problem with this design, as you all know, is it's not very efficient, especially because on most computers, this random number generator is implemented by collecting system entropy, like keystroke timings. We don't get enough randomness, which is just one problem that most people observe. But the second problem is it's very hard to analyze the quality of the randomness that comes out of these generators, because they're all different. They use hardware. It's hard to say what hardware is doing. Is it doing it right? We don't really have a good way of analyzing that. So in a modern system, the way that we build systems, the way that we build random number generators is actually to use two layers. The first layer is a true random number generator, which may use hardware. It may just be an entropy collector. And the second layer is something that we call a pseudo-random number generator, which takes a seed from the original random number generator and stretches it deterministically into a large number of bits. This is the classic urandom, devrandom design. They're not exactly hooked up that way, but ultimately that's what's going on. Now, the thing about these middle layers is they're deterministic. They're very fast, which is great when you're handling a lot of ECDH sessions, for example. And more importantly, they're algorithms that can be implemented in software. So if we're going to put a vulnerability into a system, we're going to do it in this middle component, this deterministic PRNG, also known as a deterministic random bit generator if you work for the government. Okay? So I want to take you inside of a DRBG. I don't want you to think about the mathematics of anything. I just want you to look at the block diagram of what one of these things does. Typically, the standards that we've adopted, at least the government has recommended we adopt, look like this. They involve two functions, f and g. Don't worry about what they are right now. We start with some initial seed coming in on the left, and it goes into the function f, where it's updated into the next internal state. And then that gets kicked forward through the same function f repeatedly. And if we assume that these functions have some nice properties, for example, that they're one-way, and they have some sort of random-ish property that they scramble the inputs, then what that means is even if somebody attacks this generator and gets the internal state out of it at time t, they won't be able to rewind and see what random number generators it generated in the past. So that's the justification for this top loop. But of course, we can't just output those bits, those internal states, because anyone who gets the internal state at time t can predict what's going to come out of the generator at time t plus 1. So we need yet another function, which we'll call g here, that takes those internal states and does something in a one-way, pseudo-random type of fashion, so that what we actually get out is actual output that is not related in an obvious way to the internal state. This should be indistinguishable from random, and it should not be possible to go backwards here. So this is the overview. Almost every DRBG that's been standardized uses this form depending on what the implementation of f and g is. Now, our goal is not to build a good random number generator. Our goal is to build one that's broken. But we want to break it just for us and not for the whole world. So when we start thinking about how we do that, it requires kind of a bit of creativity. The first and kind of most obvious idea, which is a very bad idea, is why don't we just set f and g to be the same function? Now, obviously, this is not going to be a secure RNG or DRBG because anybody who sees this output will immediately know this state because they're the same value. No good. But it gives us some inspiration for how we might do things in a better way. A second approach, which does not use f and g being the same function, is we make the g function somehow invertible. So it's one way for everybody else besides us, but we have some kind of trapdoor, some kind of secret value that only we know, that allows us to take a block of output and go backwards up to that internal state from which anybody can compute the rest of the outputs that are going to come out of this generator. One idea. However we do that, that's one idea. An even cleverer idea is we actually have some kind of translation function that can take the output of an f function and translate it into the output, corresponding output on the same input for that g function. Sorry, the other way around. The output of a g function translate to an f function. Don't worry about how it works, but let's imagine we had that. That means given one block of output, we could translate up here to state 2, and then we could predict every future output of the generator with no additional magic. So somehow we have to build this. How do we build it? Well, the problem is it requires us to think very hard about what f and g are going to be. The jokers at NIST, who obviously are not quite on our team, but are useful at least, have some ideas about what f and g should be. Their ideas involve using things like hash functions. SHA is a very big recommendation of theirs. HMAC, also using hash functions. And they also recommend using AES. So they propose 3 DRBGs for the standards that we're working on. Actually, we proposed the hash one, and it turns out that ours is just a little bit broken in an exploitable way, but then they come along and fix it. So that's not very helpful. So we have 3 different standards that are not obvious it's not obvious how we're going to do anything. There's no obvious translation function, inversion function that only we can exploit, as long as these things are implemented correctly. Now, maybe we can make it so they're a bit fragile so that it would be possible to implement them wrong, but it's not obvious how to exploit them. Another alternative is to use different kinds of f and g functions. We could use elements from public key cryptography where we really do have some kind of magical translation function, and that can be keyed by some kind of trapdoor that only we know, or some kind of inversion function. And it turns out that as the NSA, there are 2 recommendations we make to the standards process. One is called dual EC DRBG, and it implements both f and g using elliptic curve scalar multiplication. And then there's another one called Macaulay-Schnorr, which uses, roughly speaking, some variant of RSA, using public keys that we, the NSA, generate and tell you to use. Okay? So those are the 2 options we put forward. These are a lot more promising. In fact, dual EC has a particularly nice design in the sense that f and g are both implemented with the same operation, just over 2 different points, p and q. And it turns out that if you give me the output of g of x, if I know a secret scalar, a, and I generated the scalar when I made the points p and q, then I can very easily take the output g of x and map it onto the value f of x, and I can essentially run that attack where I translate, and it requires me to know this trapdoor that only I should know if I'm the one who generated the parameters. So this is all very well-known stuff. But for any of this to work, there's a requirement. As part of the standardization process, we have to generate the values p and q. That is, the NSA or whoever is going to know the trapdoor has to generate them. And that's a little tricky because nobody's going to allow us to put some parameters p and q into a standard without specifying where they came from, right? In fact, NIST employees are going to ask where they came from. For example, John Kelsey at NIST might send an email to the NSA's contractor Signacom saying, hey, where did P and Q come from? And that's why it's very important for us to tell our contractors, NSA has told us not to talk about it. John Kelsey didn't understand why this was significant then, but later he would understand. There is one little sticky wicket when it comes to dual EC. The problem is, and this is a little bit technical, and I'm trying to keep this very high level, but the problem is that what we're using is the output of G is not the entire elliptic curve point. It's the x-coordinates of the elliptic curve point. And what we want is random outputs. G should be putting out random or indistinguishable from random values. This was not an early requirement of this specification, but it later became one. The problem is that x-coordinates of elliptic curve points are not uniformly distributed. Only about half the points are. So we need to do something to make them look a bit more uniform. And the obvious idea is that we could drop a few of the most significant bits. And it turns out that does help the problem. And it gets better. The more bits you drop, the more the output looks like random. But the problem is the more bits we drop, the more we're going to lose. Our trapdoor is not going to work as well. So we have to drop just enough to make things good so we can still guess the missing bits and go backwards. But we can't drop too many. We can't drop too few, or it's going to be obviously biased. So we came to an agreement that maybe we'll drop 16 or 17 bits. And that does leave a bias. But what we have to do then is justify computationally that the bias doesn't look too bad. I have no idea what the axes on this graph mean, by the way. But this is part of the NSA's justification from a FOIA request of why it's OK to have a bias. This is dated about 2004, 2005. Who knows? OK, so we've given you the basic design. There's nothing new about this. This is all well known. But we have to standardize the system. And that actually does take a little bit of work. To standardize the system, we have to go through multiple standards agencies. And yes, I know this is a technical workshop, and this is going to get a little bit boring and a little bit procedural. But it's really important to understand how this worked. We don't go to NIST. We do not go to NIST because NIST might say no. Instead, we go to a third party. We go to ANSI, the American National Standards Institute. And ANSI is working on something called the Deterministic Random Bit Generator Standards for their X9 F1 Tools Committee. So we go to them and we say, well, this is our contribution. We have this dual EC design and these 2 points that go with it. And the committee, just so you know what it looks like, is it's a nice mixture of people. There's a few people from NIST, 3 people from RSA, a few people from the National Security Agency, and Certicom and Trust, some other people. So this is a rough idea of what we're talking about. So far, so good. Everybody accepts our standard. It's a private, non-public process, so nobody gets to see our draft. This is great. But then some people on the committee get finicky. And they express their finickiness in a really strange way. They file a patent. Dan Brown and Scott Vanstone file a patent on the idea of using our beautiful random number generator as a key escrow system. In early 2005, they point out to the committee that this is a problem. When the committee does nothing, they file a patent saying, hey, you can use the knowledge of the relationship between P and Q to build this wonderful system that allows a company to break every SSL connection going through their system. This is a terrific invention. This is probably the most passive-aggressive patent filing ever created in the history of cryptographic standards. And by the way, I'm assigning nothing but good motivations to this. I really think that they saw the problem here. We're not able to get traction on this very closed committee, and this was their way to get things through. So that's my theory on this patent. Patent was not public until 2007, unfortunately. But they did manage to get a little bit of a pushback, a little bit of a push on the ANSI committee. The ANSI committee then decided they were going to add a mechanism to allow you to generate your own P and Q using hash functions, which is a great idea. Unfortunately, it turns out that the NSA notified the committee that one of their partners had already implemented dual EC using the existing standard parameters, RSA in this case, which required a new solution. And the new solution was to add an optional mechanism to generate your own parameters, but use the original P and Q as the default. And this was ultimately what went forward. Once you have it in ANSI, it's only a matter of simplifying things. NIST then adopted it as part of their SB 890 standard. And then something really weird happened. I don't really understand the parameters of weird yet, but I hope we hear more about this in the future. The NSA took over sole editorship of the ISO standard, which was working on the same thing. Now, ISO already had a version of this standard. They decided one day that they were going to drop it on the floor and take the entire ANSI standard verbatim and move it over and make it into an ISO standard. I don't know why. Along the way, they made exactly one change. They removed the optional mechanism to generate your own points P and Q. That's it. And the ISO standard became essentially the same as the ANSI standard. Very strange. Well, not so strange. Actually, it's exactly what you want, but it's not so strange. OK. And then from there, everything is just implementation. You have this, you have RSA, then eventually you wind up with Microsoft implementing it, Cisco, BlackBerry, et cetera. Pretty soon, eventually even OpenSSL does it at the behest of a large defense contractor, implements this full thing. And so you've got the code out there. It's not the default in most systems, but it's out there. It is the default in RSA, but not everywhere else. Okay, so now we have to deploy this system. How are we going to do that? Well, before I go there, I want to play a video clip. I hope the sound is up. Let's see if this works.
Thank you. By the way, I also think that the mathematics...
Sorry, this is, let me go back and give an introduction. This is Dickie George giving a presentation in which he claims that there is nothing wrong with dual EC, and it was just an accident, and he kind of did it all. But I want to play this particular quote because I think it's relevant to this discussion.
Thank you. By the way, I also think that the mathematics behind the papers on breaking that are not very realistic. So, and I've talked to some of the people who've done some of that work, and their eyes open wide when I talk about how hard it is to really get the information they assume they just get to attack this thing. Not that easy. In real life, you know, it's real easy in a lab, it's real easy in a classroom, it's hard in real life because stuff just happens that you don't expect to have happen. And I've challenged any of them to actually generate their own parameters and show me that in real life they can recover that. No one has done it yet. I didn't offer them a lot of money either after them a dinner, so maybe it's not worth their time.
I think it is worth our time. So we have a paper that's going to be appearing on Thursday at the main conference where we did exactly that. We generated our own parameters and we reverse engineered a series of implementations to see exactly what those confounding factors that Dickie George is talking about might be, and also to look at these implementations and see how they could make life easier for us by removing some of the barriers. Before I just talk about that, I'm just going to talk about it very briefly because you should go to the presentation on Thursday, but I want to talk about some of the things that get in the way. One of the things that gets in the way is that the TLS spec only gives us 28 bytes of this server random nonce. Now I said I should have given you some concrete numbers. The original x coordinate that comes out of the G function is 32 bytes. Because we had to truncate, we dropped 2 bytes. So we're down to 30. That's okay. We can guess the missing 2 bytes. It's 2 to the 16 work for us to go backward and guess those 2. But unfortunately, most TLS implementations add a timestamp that's 4 bytes long to the front of the server nonce, which means we're actually cut down to 28 bytes by the time we get this value. That means we have to guess 2 to the 32 possible values for those first missing 4 bytes, and then in order to invert. That's not so great. Now, fortunately, some implementations give us an up to 32 byte session ID, which is generated randomly in some cases, so that helps us. One of the strange things is that the session ID and server nonce may come from 2 separate output blocks. In other words, 2 separate instantiations of that G function, or they may come by essentially computing a bunch of stuff and then concatenating it and then breaking it up into fields. If they compute a bunch of output and break it into fields, it's very likely that we'll get an entire block of G output with nothing missing. If they make multiple calls to the generator, then we'll end up with different pieces, and unfortunately then we have to do a lot more guessing, so that's not great. But the other thing that's really obvious is that these 32 byte numbers, these are for one particular setting of the generator, the P256 curve. If we were to use larger curves, like 512-bit curves, there's no way any of this would work. TLS does not give us large outputs. There's nothing in here that we could use to get 512 bits out of TLS. Now, before I go forward and talk about what we found, I want to introduce this term, kleptographic friendly implementation. I want to actually create an acronym for this. But in order to be kleptographically friendly, an implementation has to use this random number generated by default. It has to do something like caching RNG output to ensure that even if we get little bits of value spread across multiple fields, they actually come from one G block. We have to avoid this NIST additional input, which allows us to feed additional entropy into the system. That has to be avoided. We have to provide some unspecified mechanism to allow us to do 512-bit curves. And finally, we have to add a detection mechanism, because there's a lot of TLS traffic out there. There's no point in us spending a bunch of computational work to try to exploit every TLS session when not all of them are using dual EC. So we need some kind of fingerprinting mechanism. Those are the features we would look for in an implementation that we were trying to make vulnerable. So this is what we found. And I just want to add that Dickie George really owes us a dinner, and I can't contact the guy, and I feel like this bet needs to be paid off. One of the really unusual things we found, looking inside of the RSA BSafe product, was the presence of a non-standard extension, an unadopted RFC called the Extended Random Extension, which was written by Eric Riscorla and Margaret Salter of the National Security Agency. And roughly speaking, what it does is this. The TLS server random nonce is right now only 32 bytes long. But what we can do with this particular extension is we can make it as large as we want it to be. We can make it up to 2 to the 16 minus 1 bytes if we want. That means huge amounts of random number generator output can be revealed, solving all our problems. Even for 512-bit curves, we can get everything we need. This is implemented in only one TLS implementation I know of, which is the RSA B-Safe implementation. In the Java version, there's also API support for it in the C version. We just didn't see it in the version that we downloaded. So given all of this, looking at a collection of different implementations, including RSA, Microsoft's TLS implementation, and OpenSSL, let's compare the different observations based on those points I gave you before. How much randomness can we get per session? Well, it turns out because of the way caching is used in RSA B-Safe for C, we can get anywhere from 31 bytes to 60 bytes of contiguous randomness from any session. What that means is we can run the attack in essentially 2 to the 16 effort. For all of these others, we get only 28 bytes, which means we have to guess 4 bytes, so 2 to the 32 effort right off the bat just to get that information. This one just happens to be more vulnerable. RSA, of course, uses the default RNG, uses R dually C as the default RNG. Extended random is present in both of these RSAs, but it seems to be disabled in the particular one we looked at. And then we found that something really interesting, which is that OpenSSL implements kind of a countermeasure. This is something called NIST's additional input, where they try to feed additional entropy into the random number generator. We were able to show that we can actually break this, but it takes significantly more effort, 2 to the k times 83 minutes of effort in order to decrypt a TLS session. But overall, I think these results are all pretty good. What they show is that despite what Dickie George says, given a trace of a TLS session, literally just a PCAP, you can crack, given the trapdoor, you can crack any TLS session, completely decrypt it, using, in at most, maybe a few hundred minutes or maybe less than 100 minutes, and sometimes as little as a fraction of a minute on particular implementations that happen to be friendly. And so the only other thing I want to add, and I'm not trying to draw any allegations here or draw any ties to this, but there was at least some allegation made that perhaps RSA worked with NSA, and that's the reason they included dual EC and they made these changes. I'll leave that up to you to decide if that's true. The only thing I want to add to this, and I know I'm out of time, is I want to talk about the future. Now, I mentioned early on in this presentation that the one way you could do this without standards and without public key cryptography was to put a piece of hardware in everybody's computer. If you were to do that, it might look a lot like this. This is the implementation of RD-RAND inside of Intel. Now, I don't think that there's a backdoor in RD-RAND, but I do want to say that there are a very small number of places where if you were to replace, let's say, the key that's being updated throughout the AES DRBG cycle with a key that was not that key, was something specifically known by the NSA, you could actually probably do almost exactly the same thing. You could recover an entire session. It would be very hard to do this without getting caught, but on the other hand, it's not like there are a lot of people looking. So this is kind of the future of how a kleptographic implementation might work. Anyway, I want to thank a bunch of people for this, especially my co-authors. Please go see their talk on Thursday, and thank you all for being here.
Hi, Rick Farrow. So one thing you mentioned, but I guess you ran out of time, is you said you'd like to know which implementation you're looking at, so it's worth wasting your time on. So is that included in this when you're doing this handshake?
I totally forgot to mention, yes. All of the RSA products include a fingerprint on every RSA connection that allows you to detect which one's RSA. Yes.
Okay, thanks.
All right.
So I have a question. In breaking those complications that were those obstacles that were to stand in front of the recovering the key, do you think that the NSA may have overestimated how hard they were? Do you believe that they put their faith in those things being more complex?
So here's what I think the NSA did. I think the NSA, assuming this is for real and not just our imaginings, but I think what the NSA did is they realized that a lot of people were going to be implementing these things. And there were engineering decisions that could be made that would make them harder or more tractable. And I think what they did is they tried to build a system that was going to be exploitable across the largest number of implementations possible. And I think that many of the decisions they made kind of reflect that design paradigm.
Mm-hmm. Thank you.
Hi. So if you have, let's say, something like RD-RAND in Intel. Couldn't you actually go a hybrid way and actually, deploy a somewhat kleptography-friendly algorithm that is still not easily breakable, and then pointedly backdoor machines with microcode updates?
That's what people have suggested, that yes. So we don't, I don't know exactly how Intel controls microcode updates and assigning keys. Okay, but the only counter argument to that is that if you were going to do that, is RDRAN the thing you would go after, or are there other parts of the system that you would attack as well? But certainly you could do that.
Okay.
Thank you.